Okay, so now we're going to start to jump into what happens whenever we don't have a geometric series and we don't have a p-series. And so we go to the nth term test and we didn't prove it diverges. It equals 0, so it's inconclusive. So that means that we're going to need more tests to tell if a series converges or diverges. Let me show you in the roadmap where we're at here. So we don't have a geometric or p-series. We haven't learned alternating series yet, but we'll assume we don't have that either. So then we do the nth term test, and we get equals 0, which is inconclusive. So now we start through a series of other tests. And I have them in this order because the first one we're going to learn, the ratio test, is the easiest of these tests and probably the one that just works the best, the most. Then in this lesson, we'll also go and learn the integral test, which we will do if the ratio test itself is inconclusive. Sometimes the integral test is impossible to use or very difficult to use. And so in another video, we will go to kind of a last resort, these comparison tests. So that's where we're at. So we're going to be in this circle 4 here. We don't have geometric p or alternating. The nth term test was inconclusive. So now we're starting to learn about other tests we can do. And we're going to start with one called the ratio test. Okay, so the ratio test is very useful. You will find it will help you to determine convergence or divergence for many series. It's really useful. In fact, it's so useful, some people just prefer to do it all the time. It's a little tricky. It takes a little bit of work. It's not always the most efficient test. So here you go. The definition is a little tricky, and this is definitely one that you need to memorize. So this has got to be high on your priority list for this unit. So here we go. What does it say? Well, the series will converge if the limit as n goes to infinity of the absolute value of the next term up from your series divided by the series is less than 1. Now, this is tricky. A sub n plus 1 divided by a sub n. I'll explain what all these mean in a minute. Let's just go through the rest of the definition. The series will diverge if that limit answer is greater than 1. So look what we have so far. It converges if the limit answer is less than 1, diverges if it's greater than 1. And unfortunately, we also have another inconclusive thing result if the limit equals 1. So, you can get frustrating. You can work through the nth term test, get a limit equal to 0, so it's inconclusive. Then you go to this ratio test and get the limit equal to 1 of the ratio test, so it's inconclusive, and you have to keep going on to other tests. So a little frustrating. That doesn't happen very often. Okay, so probably the weirdest thing is what is this a sub n plus 1? So basically you add 1 to every occurrence of n in the function. So that means that you will create a new version of the function with all the n's getting an added 1. Then you're going to divide that function by the old function. So just look carefully. All these have a new function, all the n's getting a 1, divided by the old function, and we take the absolute value of all that. So the negative doesn't really matter. We'll take the limit as n approaches infinity of the absolute value of that quotient. All right, now, like the nth term test, you are only testing the function a sub n. You're not testing the actual summation symbol or n equals this to infinity or anything like that. In fact, it doesn't really matter what n starts on these. Now, number 5, note that this test will help you determine convergence or divergence for many series. This is nice. The exception is when you get an answer of 1, a limit of 1. In this case, it's inconclusive, and you'll have to proceed to another test. So I want to point that out again. We'll practice this in a minute, but what we're going to see is that if our limit is less than 1, our answer converges. If it's greater than 1, our answer diverges. So we get answers there. But if we get a limit equal to 1, that doesn't tell us anything. We have to do another test. So, question. Some people ask this. Number 6 here. If the ratio test is conclusive in most cases, why not just start with it instead of determining if a series is geometric or a p-series, or using the nth term test? And so the answer to that is that the ratio test takes a few steps to figure out. And you're going to find it easier to both rule out geometric or p-series first and to rule out divergence from the nth term test first. You're just going to find those to come pretty quickly and naturally for you. And finally, number 7, you will have to practice this test. It can be a little tricky. Can be a little tricky working with n plus 1 in the context of exponents and factorials. Once you practice it, it gets much easier. And we'll use the ratio test later in the last part of AP Calculus BC. So it's really important. So what I want to do is I want to practice this before we go on to the integral test. So let's take a series here. This is a pretty basic ratio test series. Notice it's not geometric. It's not a p-series. We have ends on top and bottom. If we want to do the nth term test, the nth term test, we might say the bottom is heavier because it's n factorial. However, 2 is going to the nth power. I'm not sure what that means. An infinite number of 2's multiplied together. I don't know. Maybe it's just not. We're not sure about the nth term test. So let's just practice our new ratio test. So here we go. So what we want to do is we want to find the limit as n approaches infinity, and remember what it is. It's the original series with added 1. So we're going to add 1 to that, all those n's. So it's the absolute value of 2 to the n plus 1 over parentheses n plus 1 factorial divided by the original series, like that. Now, I wanted to write it like that so you could see up here from our instructions, we have a sub n plus 1 over a sub n. So that's where that comes from, divided by. And so we have that fraction function divided by another fraction function. Now, what you really want to get used to doing is not writing it like that, but writing it like this. Limit as n goes to infinity, and then write the n plus 1 function, and then just go ahead and multiply by the reciprocal of the regular a sub n function. That's what you're going to do anyway, so you might as well skip the first step and just go straight to writing the limit of the a sub n plus 1 function times the reciprocal of the a sub n function. Okay, so how do we work with this limit? And this is where things get a little tricky. These n plus 1s, these factorials, maybe some things that we're not quite used to working with. So here we go. Let's take the limit as n goes to infinity. And what we're going to do, 2 to the n plus 1, remember whenever you have exponents added together, then that means that you have 2 of those bases multiplied together with each with one of those exponents. So we get that times an n factorial, so that's all of my top stuff. Now on the bottom, I have n plus 1 factorial. Well, what's factorial mean? It means that you keep multiplying it by things 1 less. So what's 1 less than n plus 1? An n. So this is actually n plus 1 times an n factorial. So all of that becomes that. You can pull that front term out. Just like if I had 5 factorial, I could pull that 5 out and say 5 times 4 factorial. Since 5 factorial is 5, 4, 3, 2, 1, and 4 factorial is 4, 3, 2, 1, I can just pull that 5 out to the front and then say 4 factorial. Well, that's what we have here. N plus 1 factorial, pull that n plus 1 out to the front, and then you have n factorial. Okay, so then we have that other 2 in there. And so what happens whenever you use the ratio test and you kind of divide things out like that and make it really nice and easy to see, you end up with lots of things that cancel out. 2n cancel out, 2 to the nth, I should say. N factorial cancel out. So this becomes the limit as n approaches infinity of 2 to the first power over n plus 1. Well, okay, guess what that is? That is the limit of 2 over infinity, which is 0. So that's 0. Now, what's that mean? Well, let's go back up to our ratio test rules. Right here, if the limit is less than 1, then it converges. So that means our series converges. So that converges by the ratio test, since our limit was less than 1. It was 0, but that's less than 1, so that works. All right, a little tricky. You definitely have to work on this. Let's do one more ratio test and just kind of get a little bit more practice here. So here we go. Let's say the summation from n equals 1 to infinity of, well, let's do something really kind of crazy looking. N to the nth over n factorial. Okay? There are a few different scenarios you're going to encounter with n's, and where n's can be powers and bases and factorials. So you'll want to make sure and practice these. All right, so definitely not geometric, not p-series. I don't even know how to apply the nth term test to this. It really seems awkward. So let's just jump into the ratio test. So we're going to find the limit as n approaches infinity. The absolute value of, okay, a sub n plus 1. So that function with every n getting 1 added to it. So that n on the base gets 1, the power gets 1, and the n factorial gets 1, n plus 1 factorial. So that's kind of really odd. Then we divide it by the original function, so we're going to multiply it by the reciprocal. Okay, so pause the video and let that sink in for a little bit. If that's a little awkward to you, you're not really sure. So here we go. Let's rewrite these, kind of separate it out. So what do I mean by that? Well, n plus 1 to the n plus 1 means that we have an n plus 1 to the nth and an n plus 1 to the first power, which we could not write that first power, but I wanted you to be able to see where I got it. And then on top we have another n factorial. Then on the bottom, we already said we can pull out an n plus 1 and then n factorial. It's a trick you want to remember. And then there is an n to the nth as well. Okay, well, this is okay. I'm not sure, oops, let's close the absolute value. I'm not sure maybe we have very much canceling out that we'd like to see a lot more cancel out. That cancels out, the n factorial, n plus 1 cancels out. And so this becomes the limit as n approaches infinity of n plus 1 to the nth power over n to the nth power. Well, that's kind of awkward, right? We're not really sure what that is. So let's see what else we can do with this. The limit as n goes to infinity of n plus 1 over n all to the nth power. Okay, so what does that mean? Well, on top we have a number that's always a little bit bigger than the bottom number. Do you see that? The top is always going to be bigger than the bottom. So, if you think about fractions and a number always being bigger than the bottom, 5 over 4, right? 7 over 6, 1,000 over 999. All of those are already greater than 1. Then if you raise them to a power, it's just going to make that even bigger. Somehow, to some degree. So what I can say for sure is that this is going to be greater than 1. And so what's the ratio test tell me? If it's greater than 1, then our original series diverges. Less than 1, the series converges. Greater than 1, diverges. Equal 1, inconclusive. Equals 1, you've got to move on to something else. So there we go. Now I do want to point out one more thing. This is kind of outside of our class, But this limit as n goes to infinity of n plus 1 over n to the nth power is actually the definition of e. So actually that limit equals e, which is still greater than 1. You didn't have to know that. We could kind of reason already that it had to be bigger than 1. Okay, so let's take a breath. What are we doing? We have learned the ratio test. The ratio test, you take the limit as m goes to infinity of the next, all the n's added to 1, divided by the original function. And then if your answer is less than 1, you converge. If your answer is greater than 1, you diverge. If it equals 1, it's inconclusive. Okay, so where are we in our roadmap? We are over here. We've already done the nth term test, or maybe we couldn't figure out how to do the nth term test, so we go to the ratio test. All right, well, we need a second part to our lesson, and that is, what if our ratio test is inconclusive? What if it equals 1? Well, guess what? You got to keep going. So we're going to try the integral test. And the integral test, it's our next choice, because past that we have these comparison tests, which are a little fuzzier. But let's learn what the integral test is. Let's just see one example of the integral test, and then that'll be it. Okay, so we've already ruled out geometric and p-series. We've ruled out alternating series, which we haven't learned yet. The nth term test maybe was inconclusive. The ratio test was inconclusive. So here we go. The integral test is more work, and should only be used if the ratio test is inconclusive. The limit goes to 1. That's really when you want to do the integral test, or if the instructions tell you to. At first glance, the integral test is a simple idea. And here's the idea. It's really an easy idea to get. A series of a function and an integral of that same function will always both converge or diverge. So this means if you can figure out the convergence or divergence of the integral, then you know you can apply that to the series. The series is going to do the same thing. Well, what's it mean for an integral to converge or diverge? Converge just means the integral gives us an answer, some number answer, right? Divergence would mean the integral gives us infinity, right? Or negative infinity, positive or negative. So the idea is simple. Here's the first thing that's not so simple. In order to even use the integral test, you have to meet 3 criteria. So for all x in our function that are greater than the term we're on, the function has to be positive. Okay, so it can't have a negative function. The function has to be continuous, which that's pretty much about everything in calculus, right? And then this is the weird one. The function has to be decreasing, meaning that our function, every time we add a new term, so n plus 1, has to be less than or equal to a sub n. The next term has to be decreasing, or really we should say non-increasing. It can be equal. But at the end of the day, well, no, it can't even be equal. I misspoke, and I'm going to erase that. It has to be decreasing. And so at the end of the day, that's a lot of stuff that has to be true to even use the integral test. Now here's the good news for AP calculus. You shouldn't have to prove. Okay, you shouldn't have to prove these 3 criteria. Now, if it's free response or some type of question that's asking you to use the integral test, you might have to state that the criteria are true. Like I can use the integral test because the function is positive, continuous, and decreasing. You just say that. You want to show it. But you need to know that those things need to happen. Okay, now, so how do we evaluate the integral of that function? Because our series is going to infinity. So that means we're going to have an integral that goes to infinity. We did improper integrals already. That was BC topic 613. So you're going to find the limit as b goes to infinity of your integral. Your bounds are 1 to infinity, 1 to b. All right. And then, you're going to have to dig into your tool bag. You're going to have to use various integration techniques to integrate the various occurrences of n in this integral. Any integration techniques that you've had are fair game here. Unfortunately, that means you might get some inverse trig answers, you might have to use the chain rule. My goodness, you might have to use, not the chain rule, use substitution. But goodness, you might have to use completing the square, integration by parts. Anything you've learned about integration is fair game here, which is another reason why this isn't like the preferred test. All right, I've kind of said this. I'll say it again. What does it mean for the integral to diverge? Its limit will go to infinity or negative infinity. Well, it has to be positive increasing, so it's going to go to infinity. Well, decreasing, but it has to be positive. On the contrary, it'll converge if it goes to any number at all. And finally, I want to say one more thing, then we'll just practice one of these. If your interval converges, the number that you converge to is not the number the series converges to. Okay? We're not getting a convergent answer. We're just answering convergent or divergent. Which one is it? We're not getting a number answer. Up to this point, this is important, the only series we've learned how to find a convergent value is geometric. Okay? So the main idea of all of these lessons is just, does a series converge or diverge? If it converges, we usually will not know what it converges to. Geometric, yes. Otherwise, no. Okay, so we're going to do an integral test. So I'm going to give you a function, a series, and we will see how it works. So here we go. So let's say that we have the series from n equals 1 to infinity, and we'll go with n over n squared plus 1. It's not geometric. It's not p-series. Maybe we could learn something about it with some of our other tests, but I want to teach you the integral test, so let's go through with it. Here we go. First of all, it is positive. You put numbers in there, you're not going to get any negative numbers. We're going from n equals 1 to infinity. It is continuous. It never breaks, and every term is less than the term before it. And really, we see the weight there on the bottom. As you get to bigger ends, the bottom is getting bigger and bigger, making a fraction that's smaller and smaller. So we are allowed to use the integral test. So I'm less concerned about knowing we're allowed to and actually just learning how to do it. Okay, so we want to kind of transform this, to the integral from 1 to infinity of n over n squared plus 1 dn. So this is an improper integral, AP topic 613. That's a BC topic. Hopefully it rings a bell, though it's probably been a little while since you've looked at these problems. So what's that mean? Well, we're going to find the limit as b goes to infinity, from 1 to infinity, of n over n squared plus 1 dn. Okay. So here we go. How are we going to integrate this? Well, it looks like we need a little bit of u substitution. So I'm going to let u equal n squared plus 1. Du is going to equal to 2n dn. And get dn by itself, I get du over 2n. So this integral becomes the limit as b goes to infinity of 1 to I'm sorry, this should not say infinity on top, it should say 1 to b. I'm going to switch both of those. I apologize. And let's see, we have n over 2n u du. And so our n's cancel out. We can bring that 1/2 to the front here. The limit as b approaches infinity of 1/2. The integral from 1 to b of 1 over u du. All right. So let's go ahead and integrate 1 over u. That's the natural log of u. The limit as b goes to infinity of 1/2 the natural log of u. We can go ahead and plug in what our u value is n squared plus 1. Don't need the absolute value because n squared will always be positive, so I'll use parentheses. And we're going to evaluate that from 1 to b. All right, so let's see. So that's going to be 1/2 the natural log b squared plus 1 minus 1/2 the natural log 1 squared plus 1. I said minus 1, maybe plus 1. Okay, so what happens here? Well, and I need to put the limit as b goes to infinity. Okay, so this is going to be the natural log of something really, really, really big, right? This is some kind of 1/2 the ln of infinity, something crazy big. And this is just minus 1/2 the natural log of 2, which is something not crazy big. So really, really infinitely big number minus something that's, peanuts compared to it, gives me a limit that approaches infinity, which is a limit that diverges. So what does that mean? That means, let's switch colors here. We'll do this bright green. All the way back here, my original series diverges because its corresponding integral also diverged. It's a lot of work. Definitely not our first choice. May not have even been our first choice on this particular problem. But that's okay. Here we go. Where are we at? So, what have we done so far? We've learned about a geometric series and p-series. If you can identify your series as one of those two, they have specific rules that are pretty quick and easy. We're not quite up to alternating series yet. We'll get there soon. But if it's none of those three, you check the nth term test. If the limit is not 0, it diverges. But if it equals 0, you got to go on. Ratio test is great. Love it. Less than 1 converges. Greater than 1 diverges. Oh, equals 1. You got to move on. And so that's where we just ended on the integral test. Integral test only works if the function's positive, continuous, and decreasing. You shouldn't have to prove those, but you might need to know those things. All right, well, what happens if we cannot use the integral test? Maybe it's impossible to integrate or extremely difficult to integrate. Then we have a last resort. We have 2 tests called comparison tests. That's coming up next. And also we will go to the other type of series that's easy to recognize but a little tricky to deal with. All right, there you go. Thanks.